lecture of logic. I should start recording first. Right. Yeah. So this is the last lecture of logic. So and then in the next lecture I shall start relation. Okay. So that topic is almost over for the relation, but there are few things I did not mention. So today I will do that. So let's share my screen. Okay, so can you see the white screen?
Yes, sir.
Yes, sir.
Okay, fine. So we have seen various types of proofs, right? So if you have a proposition, then how many ways we can proofs? We can prove those theorems. So we have seen many names there. So those are actually important. So today I shall discuss few more types of proofs, which are actually special cases of the previous proofs. So these proofs are not that much important. So the important proof was the direct proof, the proof by contraposition, proof by contradictions. So these three are the main part of these proofs of theorems. Okay. So today I shall discuss few more portions, and though these are not that much useful, but still, I mean, you should know all of these terms, and also you are familiar with most of these terms. So first one is counter examples. So this is also a part of proof. Okay. So that's mean if a proposition is given, then you can prove that proposition by counter examples. That's mean there will be some specific theorems which can be proved by counter examples. So to show a statement of the form for all x px is false. Okay. So if we want to prove that this one, that is for all x px is false, then it is sufficient to find one element or an element C such that PC is false. Okay. So this gives a proofs, right? This gives a proof of the statement for all x px is false. Now this kind of proof is called a proof by counter example. Okay. So let's see one example to understand what is it. So I am giving very simple examples because the main focus is not the examples. The main focus is to understand the types of proof. Okay. So for an example, suppose you are asked to show that the statement every positive integer is the sum of the squares of two integers. This statement is false. So that's mean we can prove this via counter examples, right? That's mean we can give one positive integer 3 which cannot be written as the sum of squares of two integers. So we take the positive integer 3. Now note that if m plus n equal to 3 for some squares of integers, say this m and n, right? Then that m and n must be belong to 0 or 1. Why? Because 0 squared equal to 0, that minus 1 square equal to 1 squared equal to 1. But if you take 2 square or minus 2 square, that will be 4 and bigger than 3, right? So therefore m or n cannot be m and n cannot be the square of 2 square, that is square of 2 or square of 3, right? So that's mean m and n should be either 0 square or 1 square, that is 0 or 1. So that's mean m and n can take only the values 0 and 1. But then m plus n cannot be 3. Plus 1 cannot be 3, right? So therefore the statement is false. So this is called proof by counter examples. Okay. So in general, if some direct proof and indirect proof does not work, then you can go for it. That is proof by counter examples, right? So we will discuss this when we will talk about the proof strategies. Now there is another types of proof. So these are the parts of the main proofs, right? So that is the reason I told you. So these are not very useful as the direct proof or the proof by proof by contraposition or proof by contradiction. So there is another type of proof, it is called the exhaustive proof. So what is this? Now if the domain is finite, then a theorem, but I did not define what is a theorem, right? So today I shall define. So what is theorem? I should define it. Okay. So if the domain is finite, then a theorem can be proved by examining a relatively small number of examples. Relatively small number of examples. I got disconnected. Okay, so am I audible, right?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fine. Now again, I will give one very easy example to understand it. Note that I am giving this very easy example. That does not mean that during exam we will ask this kind of example. Definitely not. So that will be little bit harder than this type of examples. But here I am giving to understand the statements. So prove that n plus 1 cube bigger equal to 3n if n is a positive integer with less than equal to 4. Okay. So though it is clear actually, so by observation you can easily prove that. But still I am writing this one because actually I need that. I need to write. So because that next proofs, next type of proof will be related to that only. So therefore I have to write the proof here. Now here is the solution. So that means note that here the domain is only finite, right? So since the domain is finite, so we need to verify the inequality n plus 1 cube bigger equal to 3 power n when n equal to 1, 2, 3 and 4. And we are done. So if we can prove that this statement, this part is true for n equal to 1, 2, 3 and 4, then that this theorem will be proved or this statement will be proved, right? Now this type of proofs is called the exhaustive proof. For an example, so one can easily prove that because for n equal to 1, n plus 1 cube, that will be 2 cube, that is 8, and that is bigger equal to 3, that is 3 to the power n. Similarly, for n equal to 2, n plus 1 cube equal to 3 to the power cube, that is 27, and that is bigger equal to 9, that is 3 power n, that is 3 square. Now similarly for n equal to 3, n plus 1 cube will be 4 cube, that is 64, bigger equal to 27, equal to 3 to the power n. And similarly for n equal to 4, that will be 125, bigger equal to 81, equal to 3 to the power n. Right? So therefore we have seen that we prove this theorem, right? So therefore we can say that n plus 1 cube bigger equal to 3n for positive integer n less than equal to 4. So here we used the exhaustive proof. Okay. Now note that here the domain is finite, that is fine. Also you can, if you look at the proof, then you can see that here we have only 4 cases, right? So that's mean you can divide the domain into 4 parts, and for each case you can prove that. Okay. So therefore we have another types of proof that is called proof by cases. So that is another name. Okay. So again, that proof by case, that does not imply it is a independent proof. It may be a part of a direct proof. It can be a part of some indirect proof as well. Okay. But we can say the name is that in proof by cases when there will be more than one cases will be arrived. That's when we can divide the domain into few parts, and for each part you can solve the problem. So therefore we have another term or another types of proof, you can say, that is proof by cases. So a proof by cases must cover all possible cases that arise in a theorem. Okay. Now again, I will look at a example which will be different one, so not the previous one. So we will give another example. So show that say mod of xy equal to mod x into mod y, where x, y are real numbers. Okay. So here we have proof. Now we prove this theorem or this proposition by the proof by cases. Okay. So therefore, here you can see that here we will have 4 cases. So first of all, note that what is a mod A? Mod A is, it will be A if A is bigger equal to 0. For 0 it is 0. For positive it will be only A. Okay. And it will be minus A if A is less than 0. Or you can say it is A less than equal to 0 as well, because for 0 it is 0. So therefore you can write minus A as well. Okay. So why we are writing that? Because we need that. Now to prove mod of xy equal to mod x into mod y, we have 4 cases. We have 4 cases. Okay, so first case is x bigger equal to 0, y bigger equal to 0. The second case is x bigger equal to 0, y less than 0. Third case is x less than 0, y bigger equal to 0. And fourth one is x less than 0, y less than 0. Okay. Now we first look at the proof of these cases. Then again we will conclude something. So first, how to prove case 1. Now look at if x bigger equal to 0, y bigger equal to 0, then xy, their product is, this is also bigger equal to 0, right? So thus mod of xy, that will be xy because that is positive, and also this is mod x into mod a. Okay, so this way we can prove case 1. Now if we look at case 2, now if x is bigger equal to 0, y is less than 0, then xy, that is their product is less than equal to 0. So therefore mod of xy, that will be minus xy, and it can be written as x into minus y. Now this is mod x and this is mod y. So again we have proved that. Now if you look at case 3, so if x less than 0, y bigger equal to 0, then xy less than equal to 0. So mod of xy equal to minus xy, we can write it as minus x into y, and that is mod x mod y. And if we write case 4, so if x less than 0, y less than 0, then xy is bigger than 0. So therefore mod of xy, that is just xy. It can be written as minus x minus y, that is mod x mod y. So thus the result is proved by cases, right? So therefore we can divide the domain into 4 portions, right? And each portion, that is in each part, and we have renamed it as case 1, case 2, case 3, case 4, and each case we can prove, right? So therefore the theorem is proved, and this is called proof by cases. Now note that here, if you look at the proof of these 4 cases, look at that case 1, the proof of case 1 is very different from the case 2, case 3 and case 4, right? Similarly, if you look at the case 4, then you can see the proof is different from the case 1, case 2, case 3, right? But if you look at the case 2 and case 3, then you can see that these two proofs are similar, just interchanging x by y, right? So therefore, we can merge this case 2 and case 3. So that's mean without loss, we can use a term called without loss. And we can say that without loss of generality, we can assume that x bigger equal to 0 and y less than 0. Then we don't need to do the third case. Therefore, why? Because that is similar to the second case. So therefore, it might happen that you have a long proof, and to shorten the proof, you may need to use that without loss of generality. And note that when you can use the term without loss of generality, you can use the term only if the proof of, of the portion which you are skipping is similar to the proof which you have already given. Okay. So therefore, we have a term called without loss of generality. Right. So we have already used that. So when we prove some theorem, we always use that without loss of generality, assume this. But when we are assuming this, because the portion which we are skipping is similar to the portion which we are giving, right? So we generally use without loss of generality, or in short, we just write without loss of generality, only this one. Okay. So if no additional argument is required to prove a specific case. You can say that specified case. Okay. So again, what is an example for that? So we can merge case 2 and case 3 in the previous example by saying without loss of generality, assume that x bigger equal to 0 and y less than 0. Okay, so this is called without loss of generality. We generally use, that is very useful part, that without loss of generality. So I know you already know this term, that how, when and how we should use that without loss of generality. But I know few students, maybe not from your batch, but who used that without loss of generality, but they do not understand. So why they are using that? But still, they just use that. Okay, so there is another types of proof which we have already seen. It is called existence proof. Now, what is an existence proof? So, a proof of a proposition of type there exists xpx is called an existence proof. Okay. Now, this existence proof has also two parts. One is constructive, another one is non-constructive. So you already know this, but maybe you did not notice that it has two parts. So first one is, so if we prove there exists xpx by giving an A such that PA is true, then this type of proof is called constructive. So that's when if you give one example that it is true, that's when you can find one A such that PA is true, then there exists X, PX, that statement will be true. Now this is also an existence proof, right? And these types of proof is called constructive existence proof. But that does not imply that whenever you have to prove that this one, this one is true, that does not mean that you always have to construct one A. It may happen that without any giving an example, you can prove that, right? And in that case, that is called a non-constructive proof. So a non-constructive existence proof is that if we prove there exists xpx is true in some other way. Then finding A such that PA is true. So that's when without giving this A, if we can prove the existence proof, then this is called a non-constructive existence proof. So we will give one example to see that what is constructive and what is non-constructive. So Suppose the question is show that there is a positive integer that can be written as sum of cubes of positive integers into different ways. Okay, so that's mean we need to give one existence proof. That's mean we need to find one number which can be written as sum of cubes of two positive integers in two different ways. Now we can give a constructive proof for this one. So obviously you can always run a computer program and you can find such a number, right? And you can say that this is the number. So the simplest approach is, and by hand it is almost impossible. Otherwise you have to check each and every case, right? So by computer search, one can show that if we take this number, that is can be written as 10 cube plus 9 cube and equal to 12 cube plus 1 cube. So therefore this number can be written as sum of cubes of two positive integers and in two different ways, right? So therefore this is called a constructive proof. So this is constructive proof because we are giving a particular example. Now suppose if we have a different kind of we have a different problem and it will have a different approach. So show that there exist irrational numbers x and y such that x power y is rational. Okay. So here we can give one constructive proof. That's mean we can give two irrational number such that x power y is rational. We can give such a irrational number. If you can give, then it is fine. Otherwise also we can easily prove it without giving such an example. And this types of proof is called non-constructive proof. Now you can see this kind of proof is always useful when you prove a theorem. Suppose this kind of existence proof, then you have already seen some proofs where you do not know the examples, but you know the existence. That's when existence is known, but the um, exact example is difficult to find. And here also, right, it is it is not clear that which irrational number it will be. So therefore, here we will give a non-constructive proof. So first of all, note that root 2 is irrational. Okay. Now, what about root 2 power root 2. Now, if you want to prove that this is rational, right, or this is irrational, then this is difficult to prove. So, how will you prove that? Because the tools we know, it is not clear how to prove it is rational or irrational. So, first of all, if this is rational, because if you want to give that this is rational or irrational, then you have to work hard, right? It is not immediate from this. Obviously, you can prove it, it is rational or irrational, but it is not immediate. So, you have to do some manipulation here. But if you give a non-constructive proof, then it is very simple. For an example, if this is rational, then we are done. Then take x equal to y equal to root 2. Then root 2 is irrational, but this is rational. So we are done. Now, if root 2 power root 2 is irrational, then take x equal to that root 2 power root 2 and y equal to root 2. And then x power y will be root 2 power root 2 and then root 2. That will be root 2 power 2 and that is 2, and which is rational. So we are done. Note that here we don't need to prove that root 2 power root 2 is rational or irrational, right? So you don't have to work, you don't have to find that. In either case, you can find such an example. So therefore, here this is called a non-constructive proof. So therefore, that's mean we can write here it is a non-constructive proof. So if you need to prove a existence proof, then you can give such a non-constructive proof. That's mean you are not giving any examples, but you are showing the existence. Okay, so this type of proof is very useful. It is very useful when you need to prove some difficult existence proof. Okay.
Sir,
Yes. Yes.
so here in the case like root 2 to the power root 2 is rational, then
Ah,
how we are telling that this proves that this is rational.
which one?
Sir, yeah, in the second line of the solution of this example.
No, no, no. See, we do not know root 2 power root 2 is rational or irrational. We do not know that. I am saying that here, if suppose root 2 power root 2 is rational, then we know that root 2 is irrational. So therefore root 2 power root 2 is rational. And if root 2 power root 2 is irrational, then you can take x equal to this and y equal to this, and you find that x power y equal to rational. So therefore, in either case, you can have one x and one y, irrational x and irrational y, such that x power y is rational. That's all.
Okay,
Okay, so you do
it
not
means
need
we
to prove
assume
that.
something that way.
Right. So there are
Okay,
only two possibilities that root 2 power root 2, either it is rational or irrational.
okay,
And in
okay,
either case, you will find one x and one y. So that is in this way, you don't have to prove that this is rational or irrational. In either way, you can prove that.
okay, sir.
So this
I
kind of proof is very easier, right? And suppose
yes,
you
sir.
need to prove that root 2 power root 2 is rational, then you have to do some manipulation. You have to take some, maybe you first assume it is rational, then you will find a contradiction. But you don't have to do all of this stuff here. So sometimes that only the non-constructive proof, it is very useful. But that will not work when you need the uniqueness proof. So this is the last type of proof, uniqueness. So there is you can say there are two parts of a uniqueness proof. So first one is existence and second one is uniqueness. And existence means here we need constructive. So that's mean we show that there is an X with the desired property. Okay, and uniqueness means we show that for all y not equal to x, y does not have the desired property. Again, we are giving a simple example to understand this. So show that if A and B are real numbers and A not equal to 0, then there is a unique real number R such that AR plus B equal to 0. Okay, this is a simple example. Now it should change. It needs two parts, right? One is existence. Not only existence, we need a constructive proof. So existence. So you can assume that. So you can take your R equal to minus B by A. So then AR plus B equal to A minus B by A plus B equal to 0. So we are done, right? So therefore R has the desired property, and then the second part is uniqueness. So let S be a real number such that AR plus B equal to 0 equal to AS plus B, and then AR equal to AS. Since A is not equal to 0, so R equal to S. So therefore it proves the uniqueness. So therefore it means that if you choose any other real number, any real number which has this property, then that real number should be equal to R. So therefore R is unique. So when you have this when you need to prove this kind of uniqueness property, then it has two parts. One is existence, that is constructive existence, and another one is uniqueness. Okay, so there are two parts. So these are all possible types of proofs. And I just quickly talk about the proof strategies. So actually, what is a proof strategy? That's mean if you are given one theorem or say proposition, then you need to prove, right? Now proof strategies means you need to find a proof. But in general, this is a difficult job. In fact, you can say that there is no algorithm to find a proof. So there is no such algorithm. So in general, if you have a proof, then what kind of proof will work? It is a difficult job. Sometimes direct proof works, sometimes indirect proof works, and maybe that is easier than direct proof. Sometimes you can prove by counter examples, right? So generally, one can try in that direction. So one can try first the direct proof, right? And direct proof has many parts as well. For an example, if you have conditional statements, then it has some direct proof. Now, if it is not a conditional statement, then direct proof means you can prove by cases, right? And if you have some finite domain, so you may have some exhaustive proof. Okay, so it might happen that direct proof does not work. But generally, since we should think positively first, so therefore one can try the direct proof first, and if this does not work, then one can use the indirect proof. Again, there are many parts or many types of this indirect proof. So if it is a conditional statement, then one can prove by contradiction, contraposition, prove by contraposition. And if it is not a conditional statement, then one can prove by contradiction. Now, if the direct proof and indirect proof are both do not work, then one can try with these counter examples. Right? So this is just a part. So it does not mean that it does not give any guarantee that this will definitely work. Okay. So this is just a proof strategy, how one can approach. But in short, there is no algorithm known to prove a theorem. So this is the first thing. And it is always a difficult job to find that which proof is easier and which proof will work. Fine. Okay, so first now, so this is actually the technically you can say that portion, logic portion is over. Now I define some terminology which I missed. I should define it before. When I define the proposition, maybe in the first class I should define these terminologies. Okay, and then we will see few problems. Since I have time. So first one is proposition. So we have already defined this one, right? It is a declarative sentence which is either true or false, right? Or not both. So this is called a proposition. So we have already defined it. Now sometimes we use theorem. So what is a theorem? Now what is a theorem? Okay. So theorem means you can say a major statement, or you can say a main statement. A main statement that has to be proven to be true. Okay. So what is the difference between a theorem and a question? So if I ask that show that root 2 is irrational. Okay, then that is not a theorem. It is not a theorem. Right? So this is a question. So this is a question. So what is a theorem? Theorem will be I have to remove this portion that show that. So that will be root 2 is irrational. Now that will be a theorem. Okay. So theorem means a statement which you have to prove this is true. Okay. And generally in a theory, again, what is a theory will define that. So theorem means it is a major statement. Okay. So this is name is theorem. Now what is lemma? We generally see this kind of thing in a theory, right? So what is a lemma? Lemma is actually a special type of theorem which is minor. So that's mean a minor theorem used as a, so you can say building block to prove a major theorem. Okay, or you can say that it can be used as a stepping stone to prove a major theorem. Right? Now if you look some book or some say paper or some articles, you can see that there are some lemmas. First, lemmas means there are some, this is also a result, right? This is also a result, but these are the results are minor, so it's not very important. Important in the sense that in that constant, right? So this is a minor theorems, and when you want to prove the major theorem, then you need these results. That is mean you need that minor theorems. So by using lemmas, you can prove a theorems. So that's all. Okay. So but you cannot say that theorem is a corollary of lemmas. You cannot say that because theorem mainly is the main result of that portion. And lemma is used generally not one lemma, generally very many, say few lemmas or several lemmas are used to prove a theorem. Okay. Now what is a corollary? Now corollary is again a minor theorem which is an easy consequence of a major theorem. Okay, so in short, if you look at in some direction, you will have few lemmas, say lemma. So you have say three minor results which can be used to prove a theorem, and from theorem you can have a corollary. So generally this. So this is a major result, and these all are minor. Okay, so this is a major result means theorem, and corollary and lemmas are the minor results. So generally lemmas are used to prove a theorem, and corollary is a consequence of theorems. So these are the difference between theorem, lemma, and corollary. And what is axioms? So I told it in the last time in the previous lecture when I told about the well ordering principle, right? So this is actually a assumption. Okay, and most of the case it is unproved. Okay, and it is defining structures about which we are reasoning. So you can say that it is starting point of say mathematics. Okay, so this is a axioms, and there is another term called conjecture. Now conjecture means it is a statement whose truth value is not known. Okay, so conjecture means a statement whose truth value is not known, but believed that it is true. But believed to be true. So this is called a conjecture. And the set of all these major and minor theorems, okay, which can be proved in a given set of axioms, and this collection is called a theory. So what is a theory? Theory, a collection of all. You can say when say all should be it is related. Major and minor theorems. That's mean it is collection of all of these axioms, theorems, lemmas, corollaries, conjectures, okay, and related all of this. So this is called a theory. For an example, in this course we have seen that logic theory, and the next we will see the relation theory, and then we will see the set theory in this way. Okay, fine. So technically this syllabus is over. Now we will solve few problems. Now I think you are here. Okay. Now I will ask you one simple question. This is again the application of logic. You don't have to give the solutions. You just do by yourself and give me the answer. Okay. Now this is a question. Now this kind of question will be during exam. Okay. Now I'm writing the question first. And use the logic operator here. Okay, you can prove this by case as well, but better to use the logic one, because sometimes you will mention that use only that logic operator, otherwise the proof will not be acceptable, because here we are interested that you know these logic operators or not. Okay, so obviously here also you can prove it is by case, but do not use by case, you just use some logic operator. Okay, the question is, one say boy got trapped in a say dark room. Okay. Now the room has 3 doors. So one is red door, blue door, and green door. Okay. So for an example, you can assume that you got trapped into a room which room has 3 doors, red, blue, and green. Okay. And it is given that behind one door, so one of the doors, there are 3 doors, right? And behind one of the doors, there is freedom. And behind other 2 doors, there is a death. So it is only freedom, either you will get a freedom or it is a death. Okay. So we do not know behind which door we have a freedom. Okay. Okay. And on each door, there is an inscription. It is something written on each door. So for an example, so this is a red door. So this is blue door. And this is green door. Okay. Now in the red door, it is written that freedom is behind this door. Okay. And in the blue door, it is written that freedom is not behind this door. And here it is written that freedom is not behind blue door. Okay. So this is given. So we know that out of these 3 door, only one door has freedom and other 2 doors does not have freedom. Okay. And there is something written on the each door. And also it is given that at least one of these 3 statement is true and at least one of these 3 statement is false. Okay. Then the question is, which door would lead the door or lead the boy to safety? That's mean which is the door of freedom. Okay. So this is the question. So that's mean one boy got trapped in a room, which room has 3 doors. Okay. And it is given that behind one door is freedom and behind other two doors are there are death. That's mean there is no freedom. And there is something written on these three doors. This is written on the red door, so freedom is behind this door. It is written that freedom is not behind this door, and here it is given that freedom is not behind the blue doors. Okay, and given that at least one of these statements is true, and at least one of these three statements is false. Right. So now the answer is already there are many students given the answer. Now can you quickly explain this in terms of logic? Because if you go by the cases, so first you can assume that the red freedom is behind red door, then you will get some contradiction, right? Now how did you prove that? Yes, any quick argument? How did you prove that? So there are many ways to prove this. So those who have given the answer, can you give a proof by using truth table? So if we ask that, okay, you prove this by using truth table, can you prove that? Yes, just write yes if it is yes.
So, but isn't truth table an elaborate form of cases only?
Right. So can you write in terms of that?
Yes, so we can use a truth table, but we're essentially taking cases only.
Yeah, obviously, because there are only three cases, right?
Yes, but we aren't allowed to take cases, right?
Right. Here you are allowed, but sometimes see
Oh,
some that there will be some during exam if we ask a problem. Sometimes we may ask you to specify. For an example, if we can give some compound statement and we can say that okay, prove this equivalence by without using truth table. Then you have to use some previous known or some uh, say for an example some results to prove that. For an example, you can use De Morgan law, distributive law, something kind of that. And this one also you can use the case 1, case 2 and case 3. If you use first case is freedom is behind red door, second case is freedom is behind blue door, then you will get contradiction. And then so therefore the answer will be the green door. So this is one way to prove it.
Sir, the first statement that at least one of the three statements is true can be represented by, let's say my PX is that safety is behind the door of color X. Okay, that is
Okay.
the PX. So I can write at least one of these statements is true as PG or PB or PR.
Right.
And the other one, at least one of these statements is false. I can write as not PG or not PR or not PB. And so since both of them have to be true, I'll apply
But no. You cannot say that because the written here, if you look at the what is written here, it is written that freedom is behind this door, and here it is written that freedom is not behind this door.
Sir,
Sir,
we try
sir,
doing
I
logic.
have,
You'll get
I have
like
sir.
this
Like,
thing. R is equivalent to B. PR is equivalent to PB. If you use logic.
so if we take it down like this, either like the three statements can be true or false. So if we make a truth table, like suppose all of them are saying true, then one of them is saying the truth and they are not. One of them is saying false. So we get 8 cases like that, and some
Yeah,
cases
but
contradict each other,
right.
so we
But
can
actually,
eliminate.
you don't need 8 cases. You need only 3 cases because it is already given. Yeah, basically it has 8 cases, but it is given that only one door has freedom and other two has door. So therefore, it will be either true, false, 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 true, false, or false, false, true. There will be only 3 cases actually.
Sir, I tried solving it using like logical operators.
Hmm.
I took R is
Yes, so
like
there
R
are
is the
two
freedom is behind door red, B is
Red,
freedom
right,
behind road blue.
right,
Sorry, door blue, and
blue,
G is freedom behind. Okay,
green,
so the
green, red.
first statement is R or B bar.
Right.
Sorry, R or not B or not B.
No, no, no. Yeah, you
The
don't
first
need that.
the first
Right,
statement, at least
right.
one of the
But
three
you
statements.
can say that only R or not B. That's it.
R or not B.
Ah.
And then the second statement is not R or B.
Right, exactly. And then you have only
So
3 table, 3 row.
So
True.
if you take like if you take so it's and operator if you take you'll get R and B or not R and not B,
Right.
and that is the same as this thing R if and only if B.
R if and only B. Okay, right, yeah.
So that means R and B so that means R and B have the same this thing have the same truth value.
R and B.
R and B have the same truth value.
Right. Then you are done.
But we know that this thing it is like out like it
Right. It is there are
R
only
X
3
or
cases.
G X or G is true. If both of them are same,
Exactly.
that means both of them have to be false.
Exactly, exactly. Yeah, that is a good answer actually. Yeah, that is a good answer. You have used totally that logical operators. So that is a very good one. Means if you have learned logic, then you should use that kind of operator. Right? So anyway, this is not a difficult one. And anyway, I will send you the solutions as well. Those you have not understood but your solution is totally nice. So I like that one. Okay, so there is one thing. So last time I did not have time to prove any, give any examples of the strong induction. Now again, can you, since I have time, so can you just quickly prove this one? By using strong induction. So prove that any integer n bigger equal to 2 is either prime or can be expressed as product of primes. This is also simple, but only induction will not work directly. So better to use the strong induction. So that's mean if you have any integer greater equal to 2, then either it is prime or can be represented as product of primes. Can you just quickly prove it within 5 minutes and send me?
Sir, like here, like what exactly do we define like this thing? Okay, fine. So we define prime as numbers that have only factor is either this thing one and itself, right?
Right, right, right. Yeah.
Okay, nothing else. Okay, fine.
Okay, just send me this one, then we'll stop today. And the next lecture, we will start the relation. So this is the last lecture of logic. Okay, for that we don't need recording. We can stop the recording.